Welcome back, friends, for another lecture on quantum field theory and quantum entanglement. So what we have been looking at so far has been free fields, in the sense that so far what we have looked at is starting with a scalar field, then we quantized it using equal time commutation relations. Okay, and then we got the particle picture, because once we impose the equal time commutation relations, we see that the scalar field is quantized in terms of harmonic oscillators, and these harmonic oscillators lead to you the Fock space. So you have this the fields essentially building up you the Fock space. You have one particle state in this particular fashion and giving you a momentum of p momentum states and everything. Then we also looked at the subtleties involved. We said that the subtleties involved are essentially like, this is not, the field is not really a function, it is actually an operator essentially. So distribution, okay, operator value distribution essentially. So it gives you, the reason is because these states or plane waves which are not normalized. Very good. So then we went further essentially. So then we went further. So again we started with quantization with equal time computation. So we started initially with a real scalar field or a function, okay, and then we said that it's not really a function after quantization, it's actually a distribution, because this is actually an operator essentially. Now then after doing it everything for a real scalar field and getting the particle picture, we then went to a charged scalar field, so which has 2 degrees of freedom, uh, 2 degrees of freedom. So that means you can either quantize it either in terms of phi star, or phi goes to phi 1 plus I phi 2. 2 real scalar fields, you treat them either as 2 real scalar fields, or treat phi and phi star as independent variables or independent degrees of freedom. Then we expressed pi and pi star, the relative conjugate momenta, essentially there are 2 of them again essentially, and then imposed equal time commutation relations. So this will again give you particle picture, and then you build the entire field, meaning particles and everything. And then of course this will also have the same subtleties as a single scalar field essentially. The states which we have built are not really normalizable states, but then you can build wave functions out of this which are normalizable, and typically we take a Gaussian smearing on this set of states and everything, exactly like what we do in quantum mechanics. So it is possible to build wave functions for these states, and so you can have physical picture. But the entire quantization we have done so far is for so called free fields. That means the particles don't interact with each other. So they don't interact with each other, that means they don't have any interactions, so they are not realistic. Okay, the examples so far are not realistic. Okay, they are okay. What I mean by realistic means you cannot test them, in the sense that if you don't have interaction for any particle, there is no way of knowing whether it exists or not. It should have some interaction with the nature. Okay, only then we will know whether the particle, such a particle, exists or not. Now, so the examples we have seen, in that case what happens is, the example of both the things, we didn't assume any interaction. The Lagrangian is just the kinetic term plus the mass term. Okay. Now in this case what so happens, because we are in a relativistic theory, what is happening is that the particles are, particle number is conserved. Okay, this is important to note, that the particle number is conserved because the particles don't interact with each other, so they cannot get converted one to another or so. Okay, which is possible by relativistic field theories essentially. So even though they are relativistic field theories, the particle number doesn't change. Okay, whatever state you consider, essentially that particle number doesn't change because you don't have interactions essentially. Okay, so now let's consider interactions, interacting field theories. Okay, so how do you write an interacting field theory? Let's consider the simplest possible interactions for scalar fields. Once we do fermionic fields, I'll also consider a second kind of interaction, which is called the Yukawa interaction. But right now we'll only look at the simplest possible interaction with only 1 degree of freedom or 2 degrees of freedom, like scalar fields only essentially, like the two examples we have seen. So consider real scalar fields. So real scalar fields, what interactions you can write down? So let's write down the real scalar field. Now this is the Lagrangian part. Okay, the Lagrangian, the kinetic part, and the potential part. The most general interaction you can write down here would be interaction which has phi field more than power 3. Okay, more than power 3. So that means something like pi cube, pi power 4, and keep on going on essentially. So you can have something like this. Okay. Now let's look into this. So there are quite a few things which are interesting here essentially, which are important to mention. The first one is that now you have written phi power n. So n can be a large number. I didn't say what it is essentially. N can be a large number, but it starts with 3. So phi cube means so it's self interactions essentially, and remember this thing which is sitting in front is called a coupling constant. So this is called a coupling constant. Okay, phi power n some, and this coupling constant changes. For lambda 3 it is phi cube, lambda 4 it is lambda 4, and so on. So we have different n number of coupling constants. Now should we study all possible such interactions all the way up to n tends to a large number? Now for that we have to have some sort of a organizing principle essentially. We should have some organizing principle. To do that, what I'll say is that, remember we are always working in working in natural units. Where h cross is equal to 1. So h cross is equal to action S. Okay, the action S also has same dimensions as h cross. So if h cross is set to 1, the action should be 0, dimensionless. Now action is defined in terms of del power 4 L. Okay, the action is defined in this particular fashion, d mu power 4 d mu x L. Okay, if this is the case of the if action is dimensionless, this means the Lagrangian should be of mass dimension 4 in these units. I think this is a repetition. I think I must have covered it in the earlier classes, but just for fun, let's just, in the earlier classes I must have just covered it up to the interaction, not covered the interaction part. Okay, so the dimension of the action of the Lagrangian should be, mass dimension of the Lagrangian should be 4. Putting this, we have dimension of del mu to be 1, dimension of phi to be 1, dimension of m to be 1. Okay. Okay. So with this, the first two terms are already satisfied. They have dimension 4. It's obvious, del mu phi, it's obviously. Now what happens to the third term, which is the interaction term essentially. So let's start with lambda 3. Lambda 3 by 3 factorial interaction term. Lambda 3 by 3 factorial has a term phi cube. Okay, so it has a okay, lambda 3 times 3 factorial has a term pi cube. The interaction term has further terms, lambda 4 by 4 factorial phi power 4. So lambda n by n factorial phi power n. According to the definition, the mass definition of phi is 1. So this term should total, if it is in an action, the total mass dimension of this should be 4. So the total mass dimension of this entire term should be 4. So lambda 3 phi cube total mass dimension should be 4. This implies lambda 3 has a mass dimension of 1. So if you do the same analysis by term, so lambda 4 should be already has mass dimensions 4. This implies lambda 4 has mass dimension 0. So this is dimensionless. And lambda 5 should be 4. This implies lambda 5 should be negative mass dimensions. So negative mass dimensions, negative energy dimensions, because at the end of the day what we are trying to do is build a scattering theory. Okay, and scattering always depends upon the energy of the interaction at that point, the energy of the process at hand essentially. So lambda 5 has negative mass dimension such that the total dimension of the term has 4 dimensions essentially. So the 4 dimensions. So what is happening here is that, so each term essentially, so if something has a mass dimension E, so a given process, So lambda as a mass dimension E, say for example, what it means that at high energies, okay, if you just take E to be greater than m essentially, so at high energies this term behaves perturbatively. So phi cube term behaves perturbatively because lambda is it's actually acts like a soft term. It also has various names essentially, so it behaves perturbatively, whereas it becomes large at low energies. You will realize this in more detail once we do a little bit of renormalization. The point is that, so the entire point is that whether we can treat these couplings perturbatively or not, okay. So lambda 3 term can definitely be treated perturbatively because also whether these terms are well behaved essentially with energy or not, okay. So this is at very high energies, this is some energy, and lambda cube will essentially lambda 3, what I don't mean lambda cube, lambda 3 is really a small term, so it can be treated perturbatively at high energies. Well, this is actually a rough way of mentioning it, but technically what it means essentially, okay, well, this is very heuristic arguments what I am telling you essentially to get a feel of what we are talking about essentially, okay. These terms are called dimensionful terms. These are also called soft terms. They also have another technical term which we will see, super renormalisable. So these are, each of these terms, okay, has a different meaning essentially. So the point is that this has each. Now the entire point is that even at high energies, even at, so there is also one more term, relevant, okay. So all these three words corresponding to only one particular coupling essentially. It is also a relevant coupling. That means it becomes relevant at high energies, that you cannot ignore it essentially, okay. At very high energies and the process, okay, when you are dealing with the process, then these terms become relevant, whereas the second class of terms are called marginal. They become marginally relevant. They are dimensionless couplings essentially. So these are also called renormalisable. These are also called renormalisable terms. The first ones are class or called super renormalisable. Second one are called marginal terms or renormalisable terms, and the third class has negative couplings with negative mass dimensions. They become completely irrelevant essentially at very high energies. So if you are dealing with very high energy terms, essentially meaning at very high energy process, the contribution coming from these kind of couplings is so irrelevant, you can neglect them completely. So these are called irrelevant terms. Operators. These are non-renormalisable. It also turns out to be that because they have coupling constants with negative mass dimensions, as at some point we will see, I don't know, I will just mention this. Any theory with coupling constants with negative mass dimensions, they are first of all dimension full and with negative mass dimension. So they go as 1 by g square, GeV square, or 1 by I will give you examples like Fermi theory, or there are many other examples in which the coupling constants go with negative mass dimension. Such things you cannot make a connection with physical observables, in the sense that you cannot exactly calculate it and make sure that all orders in perturbation theory that they become you can do a one-to-one matching with the experiment essentially. So there is this issue, okay, So they are negative mass dimensions. Okay. So depending upon the coupling constant, you see that there are three classes which you can think of interactions. One with relevant operators, another with marginal operators, and the third one is irrelevant operators. Okay. And we will deal all of them perturbatively. Essentially we will deal all of them perturbatively. Now the point is that for all relevant for our purposes, essentially the relevant operators which are super renormalisable do not we do not want to study them in really in great detail. Neither the irrelevant operators which will not have any physical effects in at very large energies, essentially in the UV or in ultraviolet or yeah. So what we will focus on are only these examples. Okay, these are examples which are marginal and renormalisable set of operators. Essentially we will take these examples. Of course we can do the other two also, but these are slightly more involved and everything, but as a first step we will skip the other two cases. We will focus on marginal 5-4 theory. Essentially the 5-4 theory has very important interesting physics associated with it essentially. So this theory with 4-dimensional interactions is called 5-4 theory. So this is just 4-dimensional interactions with a dimensionless coupling constant for a real scalar field. The Lagrangian looks like okay, where I drop the index lambda 4. Okay, I drop this what do you call subscript for lambda. I just leave it as lambda essentially. So earlier until now I was calling it as lambda 4 by 4 factor by 5, okay 5-4. The half factors I already explained to you, and the 4 factor is some symmetry factor which we will see essentially we will see in some time essentially. So this is the Lagrangian. Now we want to solve this Lagrangian, or we want to study this Lagrangian using the interaction picture essentially. We call it as the interaction picture. The first things we notice is that in 5-4 theory, because of the interactions the particles can interact with each other. So the particle number is no longer conserved. So if you write the Hamiltonian and look at the number operator, whether it actually commutes with the number operator or not, you see that the number operator is not conserved essentially. Okay, so the number operator, okay, the particle number the total charge will always be conserved essentially. You can okay, you can okay, there is no okay, if you are thinking of a if you are thinking in terms of a charge scalar, then the total charge also will be, we will see, can see in terms of the total charge. If you can see that the total charge will be conserved, but anyway since we have written the real scalar field, I will leave it just with the particle number. Okay, h of n the commutator is not equal to 0. So this tells you that you can actually calculate the number operator like I have said, and you can actually look into it, see that it does not commute. Okay, it does not commute. So it tells you that the number operator is no longer a definite a conserved quantity. Now given this 5-4 theory, now we need to do something called an interaction picture. Now we studied so far two pictures of QFT. One is a Schrodinger picture and the other is the Heisenberg picture. In the Schrodinger picture, operators states evolve with time, and in this, so you have I del psi by del t s is equal to h psi of t. Okay. So this is the Schrodinger picture, and in the Heisenberg picture operators do not allow. In the Heisenberg picture operators evolve in time, states remains constant. Okay. Those operators evolve in time. So you have something like, you know, operator O of h t is equal to e power I h t O Schrodinger e power minus I h t. So this is the operator which gets evolved, which gets clubbed by both sides essentially. Okay. And the relation between the states of Heisenberg and Schrodinger is the state of Heisenberg is equal to e power I h t of the Schrodinger state essentially. So this is the picture of the both the pictures, essentially the Heisenberg and the Schrodinger pictures, and you see that they are obviously they are different in philosophy, and their methodology is different essentially. In one state the operators do not allow, in other case operators evolve essentially, same with the states. Now the interaction picture on the other hand is if you want is some sort of a mixture of both the things essentially. Okay. Is okay, it is neither the Schrodinger picture nor the Heisenberg picture. So this has developed its own name. We now have a third picture which is called the interaction picture. Okay. So this is called so this is the interaction picture, which has some sort of a mixture of both the things essentially. The okay, how in some ways essentially. So we will start with the Hamiltonian. H is equal to H0 plus Hi. Okay. H0 is the Hamiltonian of the free fields. Okay, it is nothing but the Hamiltonian of the free fields, which you can derive from the Lagrangian essentially. Hi is the interaction part of the Hamiltonian. In fact, it turns out in all the cases which we will deal, L int is equal to H int. I should put dots and everything. I will come to the dots later on. Normal ordered products of the H int and L int. Okay, so we will only deal with cases in which H int is equal to L int actually most of the time. Okay, so that means that the interaction picture Hamiltonian, okay, H int Hi is nothing but your H interaction. Okay. Okay. So this is the starting point of the interaction picture, and we will in the coming class we will look at the details about how we will expand the interaction picture and derive something called the Dyson formula. How do you solve this thing for the Dyson formula essentially, and then we will go for something called the Wick's theorem before going further into the scattering theory. Okay, so let me stop here. I will come back to you in the next class essentially, where we will take up the interaction picture and go into the details about how to solve for the Dyson formula and the Wick's theorem. And so these are sort of formal topics. You may not immediately get something out of it, but these are extremely important actually. I will say, as we will also see the time ordering and everything. These are extremely important for the formal foundation of the field theory essentially. Okay, let me stop here. Thank you, and you are very welcome actually. Thank you very much.